Okay, so we are good to start. Hi, Achille. Nice to meet you. And I think lots of us are looking forward to learning about Cuspidal robots. Yeah, I'm really happy to have you here presenting.
Hold on, I can't go back to a previous slide. Oh well. That works too. Yeah, thank you so much, Matt, for having me. I'm excited to chat about both motion planning and cuspidal robots. Just a warning, this is going to be a fairly technical talk, so if you're not into any mathematics or hardcore robotics, now's the time to leave. um, and also feel free to ask questions. I don't know if there's a chat or if Matt, what your policy is. You can also keep them to the end. I'm happy to answer them. So I just made a little about me slide just to contextualize things here. In the top right, if you Google my nationality, you actually see a bunch of dogs, and I'm not too upset about that. Apparently, there's a Belgian Malinois that takes over all the attention. So I did my undergrad at the Belgian University KU Leuven, and then my master's at University of Pennsylvania in robotics. Went on to work at a company called Peanut Robotics. We made cleaning robots. Oh, and it looks like that video played. And I'm also just wanted to show this video. I'm a maintainer of the open source rover, which is officially affiliated with NASA and JPL. And definitely encourage everyone to make this. It's a super awesome platform. So just head to the NASA JPL open source rover repo if you want to make one of these. They're strong enough to pull a person, so pretty awesome. And here's a quick video, an old video of Peanut Robotics' robot cleaning a bathroom. And this is a lot about what this talk is about, because it really shows off some really advanced motion planning. This is a 7 degree of freedom articulated robot arm. And as you can see, it's doing some pretty intense motion plans. And that's when I talk about motion planning, I'm not talking about the very simple stuff that is done typically today. So really these really long wipes where you require continuous contact with the surface to really guarantee full contact. I currently am employed by a company in San Francisco called Freedom Robotics. More about that in a little bit, but we make software for operating, monitoring fleets of robots. I also, in the past couple of years, have gotten really interested in topology and differential geometry in robotics. And so you'll see a little bit of that shine through in this talk as well. And I also happen to be somewhat related to that, a creator of a open source package called Dual Quaternions, which has a ROS library as well, which is a really neat representation of SE3. So very similar, think homogeneous transformation matrices to represent orientation of position in space, but using two quaternions as opposed to a 4x4 matrix. Cool. So while I was working at Peanut Robotics, what we would often do is, and this is my unapologetic, self-proclaiming or endorsing slide. While working at Peanut Robotics, we would often be sitting next to the robot, watching it work. Literally, in the robot's in the bathroom, right next to where my ex-colleague was sitting. And we're continuously monitoring it. And if it fails, you would be ready to hit Control C or watching Arvis to see what it's doing. And as the robot gets better, you quickly go from just being ready to intercept to just monitoring it and seeing what it's doing and statistics and all that kind of stuff. And that's when I learned about Freedom Robotics, and they have a really cool platform that allows you to see where your robots are. Allows you to control them remotely, see fleet-wide statistics, and it's such an essential tool to go from one robot to 100. And so a lot of the stuff that I was doing there in the early days was building infrastructure that robotics engineers shouldn't make and software engineers should be doing instead. So this is really something that I recommend everyone to look into it or have. Cool. So a little bit about motion planning then. So robot arms, currently, I would say 95% of the robot arms today don't really use their full potential. You're looking at the workspace, some kind of workspace visualization of two robots that everyone probably knows. And what you can see is that the arm can reach each of these points, but they can't reach them in every single way. So the blue points represent the points that you can kind of reach from every angle. And then the red points are just the ones that you can reach from like one or two configurations. And what typically happens is that in real world applications, people stay away from everything that's not blue because weird stuff happens. It's typically a complicated workspace. You have boundaries, you have singularity surfaces, and even holes in those spaces, and planning just becomes a nightmare. And as I said, you can't access the full 6C space, so people just stay away from that. And what do they do when that happens? They just buy a bigger robot so that space becomes bigger. That doesn't always work in the case of lightweight robots and service robots, such as the one from Peanut that you just saw, where you mount a robot on another robot and you have limited power requirements. That's not really an option. We are seeing this in industrial robotics as well, where you can't just have infinite factory space and you want your robots to be as close to each other as possible. So you want a compact and small robot to do the task. And then, think welding robots, painting robots, going into small and tight crevices and reaching everything from left to right. Think that cleaning robot going all the way, that's not something that you can do in a very limited workspace and continuously move your robot around. So the proper solution is to look at motion planning and confidently fully use the full configuration space of your robot. So first, quickly going to blast through some approaches, 8 approaches to motion planning for a number of degree of freedom articulated robot arms. So I'm talking mostly about 6DoF, 7DoF robot arms, so 6 or 7 axes, revolute axes, but this also applies to some other robots as well. So your super simple approach is kinesthetic teaching. You tell the robot where to move from here to here, and you always stay away from Cartesian space. So you just tell the robot where to go, and you replay that with maybe some trajectory generation later. And this is awesome. Like this just works. Like you're not going to hear me complain about this approach. Singularities just don't exist. You don't have to worry about them. Things just work. So I'm not saying that this is a bad solution. This is absolutely awesome. And it is the reason why this is used most of the time. But no, if you want to define a path in Cartesian space, say you want your robot to go down a straight line or follow a path like a welding path, of course that doesn't work. And so the typical approach for that is to use Jacobians and implicit optimization. And just a quick reminder of what that is. A Jacobian, think a generalization of a gradient in multiple dimensions. And if you don't remember what a gradient is, think a generalization of a derivative for multiple variables. So what exactly the Jacobian is, if you have your forward kinematics definition, so going from joint values to end effector, XYZ roll pitch yaw, or your SE3. Then the Jacobian is the mapping of the tangent space of those. Is the derivative of that map between those two spaces. So think a map between the Lie algebra of SO2 to the power n, with n your number of degrees, and SE3 for the slightly more math inclined. And so that works great. You at each step invert some matrix and then apply that, and you can kind of get like a small incremental motion on your robot arm. So the Jacobian depends on the joint angles at each pose. I invert that matrix, take a step in that direction, and you kind of start following your path. That works great for 6 degree of freedom robots. For less or more, you kind of have to make some small adaptations, but it'll still work. Problem with that is you'll say, okay, well, what about singularities? If I'm passing through a singularity, what happens with that Jacobian? Well, what happens is that it becomes rank deficient. So the rows become linearly dependent, and you can't invert the thing anymore. And so you'll say, okay, well, I can either do the pseudo inverse, or I can just add a term that maximizes manipulability. Smart. So now I just stay away from singularities. And then someone will say, well, what about joint limits? Because when I do that, it tends to get stuck next to a joint limit. And you'll say, okay, cool, I'll add joint limit avoidance and avoid getting stuck. What about self collisions? What about external collisions? So you just start adding these implicit optimization terms to this equation at the top left, and your robot starts to work okay. And this is what is used today a lot. The issue with this is that you need to tune this. So if you're still close to a singularity, it might be that your controller starts oscillating, and that's not great. It's not very safe. And again, there's also ways to deal with that, but it just becomes exponentially complicated, and no one likes tuning. And the other issue with it is that you're not actually at the position that you want to be anymore. Your robot will now, when you're close to singularity, kind of start deviating away from it to avoid it. And so if you're welding a car part, you don't want to start like going south while you're welding a straight line. So that's a real issue. So let's look at a different approach. What if we take our paths in Cartesian space and go back to inverse kinematics? Cool. So we use a nonlinear solver. The default one in ROS would probably be track IK, which uses Newton's plus sequential quadratic programming to find, it runs those things both at the same time to find an IK solution using some kind of seed that you tell it. And then you just keep doing that. So it's a greedy algorithm. I'm going to do that at the start. I find an IK position. And then the next position, I'm going to use that previous solution to seed a new position, and you just keep going. And that actually also kind of works. That works great when you don't have a closed form solution to your inverse kinematics, and especially that's the case when you have like a snake robot with 10 degrees of freedom or more. And so again, a bunch of issues with that. You only get one or two solutions. It's so slow. It's it could take you on the order of hundreds of milliseconds sometimes to find a solution, depending on the complexity of your robot arm. You get these things because you only find a couple of solutions when your robot arm is going all the way from moving from the left to the right, and you now have to flip your elbow. You get a joint jump, and so your robot will do something weird to get there to keep going. And you just leave your path in that when that happens. And again, you're going to destroy your weld, maybe even your tool on your robot arm and also the part. It's still a gradient descent solver, so there's some randomness involved in there sometimes. And good luck building a CI/CD testing pipeline for that. Next approach. You solve your inverse kinematics analytically. Hooray, you've probably seen that in your Robotics 101 class. You solve the forward kinematics, so you get 3 equations, and then from there you have a bunch of angles, and you try to figure it out. You do some kinematic decoupling, or you use geometric insight to find what your joint angle should be. honestly, when I graduated from grad school and had taken that robotic class, I thought that was the solution that worked for everything. Turns out that's not the case. It only works for a couple of simple cases. In the real world, you hope you have a spherical wrist. You use something like FastIK, which is a analytical server solver, which works really well in some cases and works okay in a bunch of other cases. Or you plow through the math and figure it out, and that can take pretty long. The great advantage of this is that solving a single IK solution can take like 30 microseconds. We are talking like orders of magnitude faster than doing nonlinear IK solving. So the default like move it solution. So this is pretty awesome. If you can do this, by all means, please use it. And so that wasn't really motion planning. That was just solving IK and then saying, okay, we're going to do our greedy next step and maybe pick the closest solution. You'll still get stuck in cases that sometimes the entire motion planning problem itself is highly nonlinear, and just picking the greedy next best solution will definitely get you stuck. So what do? You construct a big grid over your space using all of those hopefully analytical inverse kinematic solutions that you found, and you A-star search or Dijkstra search your way through it. And that's actually pretty awesome. That works very well. There's a couple of companies and open source tools that do exactly that. And you can also use this PRM, this roadmap that you've created to do really fast replanning. So speed up your searches in the future. Again, awesome, but it must come with a disadvantage, and that disadvantage is that you get the curse of dimensionality. You now have to create a roadmap in RT that's very highly dimensional, and that problem just blows up the higher your sampling rate and the more degrees of freedom that you have. So next approach, optimization. Yay, you solve your entire problem as a nonlinear optimization. And that's something that a lot of solutions exist for. Just to mention, TradgeOpt and Chomp, I think, are the most popular ones. The awesome thing about using optimization is that you can immediately add constraints on your velocity, acceleration, jerk profiles. So you don't need to do like the sampling-based algorithms, a separate trajectory generation step where you go from positions to also velocities and accelerations for each of your joints. So that's great. You get continuous paths in all derivatives. It also works just fine for redundant robots. So there's nothing special that you need to do there. It can be pretty fast, but again, you need to deal with tuning, and you can get stuck in local minima. So, unsurprisingly, hybrids, you combine sampling and optimization-based planning. So you do a coarse sampling step, you find a number of very different solutions, and then you use nonlinear optimization to refine those solutions. And there's, again, an open source tool for this that I think is under development by SWERI, so the Southwest Research Institute, called Tesseract, and it's kind of like a move it alternative that will allow you to combine a sampling and optimization based step. I would say here be Dragons combining two pretty advanced motion planning algorithms can be a lot of work, and this is not something that like the general robotics company whose product is not motion planning will want to deal with. So I thought, well, we've solved motion planning. that was easy. So we had this robot arm that wouldn't do the full cleaning paths that we wanted to, and we just kept throwing more and more motion planning at it. And eventually, you should be able to solve any motion, right? We thought that too. So here's an example of a really old robot that we used with a Canova Miko arm, 6 degrees of freedom. And what's happening there is that it was supposed to clean this entire sink nicely, just follow a circular path. And also please excuse the old tooling. And what happens instead is halfway through the path, it suddenly decides that it needs to leave the trajectory. It goes, while it has to go here and follow that sink line, it just jumps and you see one joint completely rotating to get to the next point. And so, turns out that we haven't fully solved the motion planning, or there's something inherent to the robot that we just can't solve our way around using more motion planning and more math. And it turns out that that's the problem. So next slide. This is the part where we actually start talking about Cuspidal robots. This is what you came for. So the conventional wisdom about changing posture, and when I say posture, I'm talking about if this is your elbow up solution to this end effector position, if I want my fingers to be exactly here, then there's also a solution like this, right? So these are two postures, two inverse kinematic solutions to the same pose or position. Just like this robot, you can see on the left side, it's at one posture, and on the right side, it's at the same position. We're only with working with a three-dimensional robot here. But it's a different configuration. And along with that, you also see the manipulability of ellipsoid, which happens to be also an indication of how close or far you away from singularity. A singularity, again, being a particular configuration. So singularity is not related to the end effector position or orientation. It's an attribute, if you will, of the configuration, so how the robot is positioned. And in the case, in the middle figure here, you can see that how it completely went flat. So there's no room for the robot to move in those directions, to produce a force or direct velocity in those directions anymore. So to go from that elbow up position to the elbow down position, naturally, if my hand was a robot, it would have to pass through that singular state, through that stretched out state where it can't produce a velocity in this direction, and to get to that other pose. And that was actually proven in 1993 that should be the case in this paper. This was actually for parallel actuated manipulators, but doesn't matter. What's funny is that in 1988, a couple of years before that, someone actually came up with an example where that's not the case. They found their robot, a 3 RPR parallel manipulator, which is kind of think like multiple robot arms pushing the same, kind of like a Stewart platform. So these guys, Innocenti, Parenti, Castelli, found that there existed a robot where you can pass, where you can go from one configuration to another. And I'm using configuration and posture interchangeably. And then a year later, they also found a different type of robot that had the same ability. And then a year later, or a little bit later, Wenger and Chabot came up with or introduced the word cusps in a paper, and that's eventually we'll see where the name Cuspidal comes from. So that's some funny history and proof that science doesn't always go linearly. There's some jumping back and forth there. So now let's dive into a real example. Of course, this is a Cuspidal manipulator. I'll give that away already. It's a super simple robot arm, right? Rotation on the first joint, that's vertical, and horizontal on the second, and then a vertical again on the third joint. And so this is an orthogonal 3R manipulator, and there's a little bit of an offset on that second joint there with D2. And I've also given you the forward kinematics there, so going from the joint positions to the end effector positions again. So nothing special about that robot. So, but we already know that's cuspidal, so let's find out what that means. So we'll start by finding the singularity surfaces of this robot. And the way that you find that, you know that that a robot is at a singularity if the Jacobian is is linearly dependent rows, and so that also means if the determinant of that matrix equals 0, then you know that you're at a singularity. So that defines a surface, and so that's the equation of that surface there, and that turns out to be independent of theta 1. That kind of makes sense. You spin your robot around, that doesn't actually affect if it's stretched out or not, or if it's at a singularity. And so we can plot that in theta 2 and theta 3, and you get these nice surfaces, that expand infinitely left and right and up and down. You just stack these figures on top of each other. And we can call the non-singular parts aspects. There's two aspects here, 1 and 2, separated by the blue singularity surface line. So if you're walking along those lines, that means that you're continuously on a singularity. And we'll try to solve inverse kinematics for that. This is one of those examples where you thought that your simple robotics 101 could teach you how to do this. This should be easy. That's totally what I thought. It's not. Good luck trying to solve this just with pen and paper. But I've actually fed this to symbolic solvers of many brands, and the symbolic solver will sit there for a couple of hours and just spit out something very odd that's not correct. But there's also this theorem that says that all robot arms are 3 degree of freedom robot arms are exactly solvable. So there is a solution, and it turns out that one way to solve these things is to say, I'm going to substitute these variables to try to get rid of the sine and the cosine by going to introduce a new variable v equals tangent theta over 2. So that the tangent half angle, as it's known. And if you do that, you get a quartic polynomial. And this is, again, illustrated in that book by Selig, Geometric Fundamentals of Robotics. A quartic polynomial, you say, what's that again? That's a fourth order polynomial equation as it's portrayed there. And it turns out that also has a quartic discriminant. Think your quadratic discriminant, b squared minus 4ac, but for a fourth order polynomial. And there's also explicit solutions for this. This is, by the way, the highest degree polynomial that you can solve in closed form. As soon as you go to 5th degree, that's been proven in the last century that is not, in general case, solvable analytically. So, fun side fact. So you get these pretty complicated equations, but yay, we turned our forward kinematics into a single quartic polynomial, which we can solve for explicitly. And when we do that, we can actually plot these singular surfaces in the workspace. And you should look here on the figure on the right first. We define rho to be the distance from the origin. So if I got my robot here, arm swinging around, then it's that distance from the end effector to here, and z just to be the height of the manipulator. And it turns out if we do this, that we can plot this in a plane, and that's just nice and convenient to look at. But if you want to look at it in 3D, it's again, it doesn't depend on the angle, and so you get this nice 3D surface that just represents the same thing as the figure on the right. So pretty figures. So let's now we have our inverse kinematic solutions, and so let's test them. We'll pick a point on this odd-looking figure. Again, on the left side, you see the robot arm here, but in stick figure format. because my graphing skills aren't that excellent yet. And so that green point represents these green crosses here. And in the middle figure, you're seeing again that singular surfaces area, surfaces plotted, and that same solution. So this is, think of this as the same workspace, Cartesian space as this, just kind of squished down in 2D. And then these are those same singular surfaces that we were looking at earlier, the same surfaces as these, but in joint space. And so there's, in this area, there happens to be 4 inverse kinematic solutions to this point, to this end effector position. And you can see them here in all colors. And that is represented by these 4 crosses here. And so the astute eye has already seen that these points here on the right side are connectable without crossing a singularity. So we've already proven the existence of cuspidal robots at this point. So let's take a look at what actually happens when I go and now connects these points. So I got on the left side my manipulator going through what is a cuspidal motion. So it's going from one singularity to another, posture to another without actually passing a singularity. So you can see on the right, it's not passing a singular surface. You may ask, why is it passing a line here on this plot then? Because those are also supposed to be singular surfaces. And that is because this is a condensed representation of this, right? There's 4 solutions here, there's 2 solutions here. And so it's actually passing, think of it's like picking up the line and passing under it, and then picking up the line again and passing under it. Cool, so I think that's the same video. So that doesn't mean that a cuspidal manipulator always has the ability to do that. So, or always does that. So here's 2 different of those points. So I just, instead of picking the one on the top right, I picked one in the bottom, and I do cross the singularity. And that you can kind of see what it does. It's not fully captured in the figure, but it stretches all the way out, comes back to that same point, and crosses through a singularity, through a singular surface. Cool. And here's another one passing where I just figured I'd show you all the videos. Another 2 postures that are connected, and it now touches an internal singular surface. And so it stays within that 4 inverse kinematic solution area the whole time. And it doesn't make as big as a motion at that point, but it's still singular. Cool. So what that actually tells us, and this is where it gets a little bit more interesting, is that these singular surfaces aren't the only things that are separating these inverse kinematic solutions, these postures. So there should be other surfaces in some way that separate these, right? And they do exist. They're called characteristic surfaces, and I'm not going to go into much detail here. But these characteristic surfaces, so they all have one of the inverse kinematic solutions, create so-called reduced aspects. And if you combine these reduced aspects together nicely with these aspects that we were seeing earlier, you get these areas called uniqueness domains, where there's only one IK solution that exists if you move across that space. Kind of the same type of IK solution, if you will, the same kind of type of posture. So think like your elbow up versus your elbow down solutions. And what's cool about these really interesting looking surfaces, so this is the same figure that we were looking before, just with these in gray, these characteristic surfaces creating these reduced aspects, is that they actually tell you the regions of feasible paths. So that's interesting. If we now say, okay, well, what if I pull this this surface that we have created, and just plot the reduced aspects and kind of lift it in 3D so we can see it better, you can see how here you can go from one posture to another. So the same thing, kind of like, what I was saying earlier, where you lift up that surface and you kind of go around and under. That's what's happening here, and you're not crossing a singular surface. And but even more, you ask yourself, what am I doing if I'm going over a cliff like that? Then, in the top figure, if I'm going here from over that sharp edge and I fall down, or here, you can do that same motion and you don't fall off a cliff. But if you do that on the right side, you do fall off a cliff. And that's interesting, that the idea that feasible paths exist also means that there's such a thing as infeasible paths. And now we're getting somewhere interesting, where we were seeing before, hey, like I thought I've solved my motion planning problem, but still there's these really simple straight line even paths that I want to do, and I just get thrown off a cliff. And what happens here, if I say I'm going to just interpolate this point to this point, is you'll see your robot do like that, a nice swirly motion that I typically call a joint jump. So yeah, more animations. What if we actually do that? Of course, that's confirmed by this figure. I'm just connecting a straight line between these 2 points. The first one is fine, and then the second point you see on the left side, that blue robot just completely jumps from one configuration to another. So let's see that again. Just going through this point just fine, nothing happens, continuous, boom, and I jump to a completely different space in the configuration. And this is cool. I just want to reiterate, there's no motion planning that you can throw at this to solve this. This is like inherent a problem with, or I wouldn't say problem, a characteristic of these types of robots. So naturally, you want to ask, how do I know if the robot that I'm using at work or for my project is cuspidal? And I give a couple of pointers for this in the blogs that I've written. Just Google Medium cuspidal robots, and you'll find them. And the reason I don't say it, an easy algorithm to find out is that it's because it's largely an unsolved problem in robotics. There's no one who's like, here's the equation to figure out if your 6 degree of freedom robot is cuspidal. But there's some really good indications that you can get an idea if your robot is cuspidal or not, such as a non-spherical wrist. So a wrist where the 3 axes are intersecting at one point. For that 3R robot, we can tell it if you construct that quartic polynomial and that has 3 equal roots, you can prove that. Then you know that there are cusps, and that's a sufficient indication to tell you, but not required indication to tell you that your robot is cuspidal. And so are these cuspidal robots real? Is this just like a mathematical construct? No, there's been numerous robots that have been created, sometimes unknowingly by the designer, that these were cuspidal robots. The robot in the bottom left, after a year for unknown reasons, was taken off the shelf. In formal interviews I read somewhere, they said that they had some motion planning problems with it. So I'm not surprised. And in the middle robot, that's a robot that you can still buy today. And there's also more. I've actually seen a couple of people who had a regular non-cuspidal robots have done any modification to the joint lengths and have created themselves a cuspidal robot. But is that bad? No, not necessarily. That Canova Migo is an awesome robot, and it is used in many cases where you never run into a cuspidal motion whatsoever. And you can actually get some advantages with these robots. I think when ABB created that robot back in the day, they took it back off the shelf. They could have reiterated on the design with this knowledge of cuspidality and created a robot that would fit all of the constraints that they had and the optimizations that they wanted to make, but that wasn't Cuspidal. And so it's really good to have an understanding of how this works. And for example, if we take this Cuspidal robot that I was just showing, this 3 degree of freedom robot, and we change the link lengths a little bit, what you get is a same singularity surface, the singularity surfaces that you're seeing in the top right that don't have cusps at all. And you can actually tweak them such that you get maximal overlap of your 4 IK regions. So it's actually possible, it's not shown here, in that left figure, to make those 2 surfaces be the exact same and have full 4 posture, 4 IK solutions for each region. So that's super interesting, and that should interest you, especially if you're selecting new robots that you want to use, or if you're even designing one yourself. So I said 8 approaches at the beginning. We only looked at 7. This is, again, interesting because we've now looked at these things called reduced aspects and uniqueness domains. And what they tell you is that there's an interesting way to say, well, as opposed to doing like just this random sampling or this optimization, what if I have a really solid understanding of the geometry of my workspace, the geometry of my configurations, and I can say from the start, if you give me a path, this path is not going to work. I just cannot do it. Or I can say, yes, I can do it, and it'll pass through these 3 reduced aspects, or these 3 components, and your path has to kind of cross these boundaries. And so this is something that's a topic of active research. I think if you search around, you'll find a couple of interesting papers, and is probably something that can be combined really nicely with something like an optimization-based planning package. And then that good old book in geometry that I had bought myself a couple of years ago, and only started realizing of its importance not too long ago when I took a good look at the cover and realized that the first figure actually represents a toroid where with a path circling the cusp. So this is that book was telling me about cuspidal robots years before I realized. So there we have it. Any questions?
Thanks a lot. I bet there will be some. So the way we will do it with the question is I will allow everybody to unmute yourself. So if you have a question, please feel free to unmute and ask it. Or if you don't want to ask to record your voice, then just type your question in the chat and I will read it out loud. Sorry, I cannot find the way to allow everybody to unmute ourselves. 1 sec. Yeah, we are sorted for the questions.
Hey, can I ask a question? So I wonder, are there any classes of robots that are definitely not cuspidal? Because I'm not sure if I can completely wrap my head around this just yet. So I might have to go over the recording in a couple of weeks. But are there classes of robots that are definitely not cuspidal? So if you determine somehow that your robot has this cuspidality feature, I guess, what's an easy fix for that? So can you, for example, just add another joint to it to say if to this third link of the 3R robot you showed, can you add another rotational joint to it and lose the cuspidality? But then, of course, you trade that for higher dimensionality and a different problem. Can you always do that, or?
Great question. If you have the ability, if you have a cuspidal robot, then and if you're not able to change link lengths, so you're not able to play with those, with how long each of the distances between the joints are, then there's not anything that you can do in terms of adding more joints. Taking away a joint, on the other hand, would maybe help with that.
Yeah.
But what's actually striking is that if you were to, and this is not mathematically founded or proven in any way. This is a product of my intuition that I've built up over the last years with this. Is that if you would have a random robot generator, that most of them would actually be cuspidal. What you find is that if you have a simple 3R robot, such as a 6-stop robot, like most of the industrial robots and cobots that you find on the market right now, so the Kinova, Jayco Gen 2, or with its 6 degrees of freedom, most of the ABB lineup, FANUC, all those
2Rs.
is that they have a spherical wrist, and that allows you to do kinematic decoupling. And then you can actually, that also counts for a cuspidal robot. So you can take the first 3 links and joints and look at those to determine if you have a cuspidal robot. And then this analysis that I just did will apply. And if that's a robot that looked exactly like the one that I showed, orthogonal, where each of the axes are orthogonal to one another, but there's no offsets, it's not going to be cuspidal. If you have that same non-offset first joints, but you add a non-spherical wrist like the Kinova Miko, which had 45-degree angle joints, then it will likely become cuspidal.
Right. Okay. Yeah, very interesting.
So bottom line, typically you shouldn't be worried. There's a couple of cases, the robots that I showed, there's probably a couple of more that I haven't seen yet, that are some weird configuration, but most of them are going to be non-cuspidal just because people don't really innovate in robot arms anymore. They must be the same.
Yeah. Okay. Thanks.
Absolutely.
I have a question that would be probably connected. If you looked at some robotic arm, so for example, you were on the market to buy some arm, how would you determine that it's not cuspidal? Would you ask the manufacturer, or would you try to get the dimensions and check it yourself before buying? Or would you just buy it and test it?
That's funny. I actually did that, and I talked to a number of robot manufacturers, and it took me a while to get on the phone with the right people, the engineers, the people who actually know about robotics in some way, and they had never heard of this before. This is so unknown. Asking a manufacturer is like just not gonna yield much. I mean, I hope that after this talk, maybe some people get aware of it, but I doubt it. So yeah, it's mostly up to you to go and figure it out. I would say the best thing that you can do is simulate, and that's just true in general. Is build out your motion planning stack before you actually have the robot and see what it does. And if there's just weird motions that are happening, and that you have a weird configuration, such as offsets, non-spherical wrists, then it might be cuspidal, and it could be good to get a different robot. Again, I'm big fan of cuspidal robots because I think they're super interesting. But yeah, if you're just doing a super simple application, and you don't want to deal with all that complexity, I would stay away from them.
Okay, cool, thanks. So yeah, my the reason I'm asking is there are quite many manipulators right now that are close to DIY grade that cost about $2,000, for example. So for them, I think it might be very useful to know what you are getting yourself into.
I think so too. There's definitely some, outside of the industrial robotics space, there's a lot of low cost robots getting made, like you're saying. And if anyone should know about this, it's definitely them, because it's easy to just, it's actually pretty hard to make a robot that doesn't have offsets. And because you want to have your motor and then a link attached to it. And so you would have to like offset that by having a motor that's inverted and so on. And so it would just be easier to have that offset. And it's not like offsets mean cuspidal robots. You can perfectly have, those figures that I was showing earlier. Where is it? Here on the top right, those both have offsets. And they're not cuspidal. And so as a robot manufacturer, they should at least know like we're staying in that cuspidal, non-cuspidal zone, unless they're actually trying to make one.
Pretty cool. Loy had a nice comment in the chat. He said, "Poor ABB sales dude getting asked about cuspidality now."
I didn't quite hear that. But...
yeah, Loy is feeling sorry for all the ABB people that will be getting questions about this right now.
I actually talked to the now retired ABB engineer, and had a conversation with him about it. And I basically had to show him what we were talking about. And it could be that ABB nowadays, the younger engineers know about this. And I have no doubt that they have some really smart people that have a sense of what this means, but I wouldn't be sure if they have the like mathematical understanding of what they're actually seeing. So I think they just kind of reuse the same configurations that they've had and are not producing any awesome new change designs anymore until it's like properly tested.
I was just thinking about if you were to go buy an ABB robot and just ask the sales, is this robot cuspidal? Then the guy with the tie is going, what are you talking about?
I would advise you to not go down that path, because then you have to give them the entire presentation that I just did.
Yeah, again,
tell
they'll
them
just
what
run away.
Robots are, and then they'll tell you, "Oh well, I guess I'll check with the engineers."
yeah, exactly.
And you'll never hear again from them.
Yeah, I guess. Yeah. Cool.
I have a quick question on the I guess the path planning methods that most industrial robots are using today, because you kind of described like the IK and the Move It planners, and there's some open source stuff with the Tesseract. But are most like robot arm manufacturers sort of like custom building their own like path planning solutions, or are they like incorporating a lot of the open source stuff and kind of like branching it to tweak it for their own purposes?
Yeah, I mean, I can't speak for all of the brands that are out there. I think, and there's definitely the whole spectrum of manufacturers using pretty simple stuff to more complicated stuff. But from what I've seen, they mostly use that second approach, which is the Jacobian base approach for their Cartesian planning. But most of what they do, if you have a robot doing pick and place, a lot of that is just joint space planning. So you just kind of know this is where my robot has to be, and then to pick up, and then it needs to drop it off here. And so you already know those positions in joint space, or you've even taught them like moving the robot around. That just gets you just do your interpolation basically in joint space. There's a lot of times that gets combined with some kind of Jacobian based planner for short segments. So just going in and out to do a pick and place. And that's typically fine, even with the cuspidal robots. It's like you saw in the video, when you're doing those really long motions, that you will inevitably hit a boundary and need to do like a crazy switch. So
cool. Very cool.
All right.
Okay, if we might be, if there are no more questions, I have one more, my favorite one. it's not related to this problem necessarily. Maybe it is, but in your career, did you run into any mind-blowing issues? So from some people, I think the theme that keeps coming back is that the robot for some reason started running away. And yeah, the stories are usually quite good. Do you have anything like that in your mind?
I mean, this is definitely that motion planning problem that we were running into was definitely a big in the discovery of cuspidal robots for me was definitely a big one. But I do remember a time while at Peanut Robotics that we were cleaning a hotel room, and we were monitoring the robots. You know, there's a binocular camera sitting on top, so we can see a pretty much 360-degree field of view around the robot. And the the cleaning staff of the hotel arrives, and there was what followed was a fierce comparison of the cleaning staff and our cleaning robot, which we were able to follow remotely, and they had no idea that we were able to see that. So that was an interesting point in my career.
Yeah, sounds interesting. All right. If there are no more questions, it's your last chance to ask it. If you have one more, maybe.
If there's no questions, that means either people had no idea what I was talking about, or it was really well understood.
I think, yeah, it's good to digest. At least for me, it's good to spend some time thinking about it, and then probably I will keep coming back to this.
Yeah, and again, this is all in the Medium blog, so it's a little bit more digestible there as well.
Yeah, and I think this presentation can be, so I will upload it to YouTube. So if someone needs, maybe it will provide some other angle to some people with you explaining it. All right, so let's get going. I want to let everybody know that this is the last presentation in what I would call a season. I don't have any talks lined up, but I'm hoping that we'll come back in September. So in the chat, I'll just drop a link. If you had time to give us some feedback, that would be amazing. Other than that, I guess we'll see you guys in September. Many thanks for the presentation. It was super cool. And if you have any follow-up thoughts, let me know, and I'll be more than happy to share it in the newsletter or in one of these meetings.
Yeah, thanks. Thanks for organizing and all the meetings so far. I have one more question, by the way. So I was going over this Medium blog post to recap, but you mentioned that in this region there is a maximum of 4 IK solutions. So probably I missed it, but
for 3R robots, yeah.
So for 3R, oh right, yeah, okay. So if you have one more degree of freedom, that becomes say 5 or 8. I'm not
8.
sure.
Yeah. Up to 8. It depends on the configuration. Again, you can make a 3R robot that has 2 solutions everywhere.
Right. Okay. Yeah. Okay. Well, I have to go over this a bunch more times. Right. Thanks.
Actually, I'm not entirely sure about the 4 degree of freedom. I think it's 8, but yeah, don't quote me on that. I think I've seen 6 soft robots with 16 solutions. So,
right. Yeah, but at least a finite amount of solutions, because I don't think it's either. Yeah. Okay. Of course, it's either finite or infinite, but obviously, but a low amount of relatively low amounts of IK solutions. I guess if there's thousands of IK solutions, then you might as well be infinite, I guess.
Yeah, as soon as you have thousands of IK solutions, you're probably talking about a 7 degree of freedom or higher robot, and those
Right.
can have infinite solutions. So actually, the one of the figures that I showed were the inverse kinematic solutions for a 7 degree of freedom robot, the
Right.
Canova Jaco Gen 3, and they have infinite, up to infinite number of solutions.
Yeah. Okay. Yeah, because I've been working on a robot which had, if I recall correctly, 8 or 9 degrees of freedom. So that was quite complicated, but then also had a bunch of constraints to reduce it again. So I think it is determining if that would be Cuspidal or not. But
yeah, I mean, if it
idea.
had multiple constraints, that kind of reminds me of a parallel robot. And that was actually one of the first robots, the robots
Right.
where you have like two things driving the end effector at the same time.
Yeah.
And those can be cuspidal as well. Those are actually the first robot to be proven to be cuspidal was a robot like that.
Right. Okay.
There's a couple of researchers that are active on this this domain. I would, if you're really interested in diving in deeply, and some of the figures I based off and recalculated or edited from Philippe Wenger, who's a French researcher.
Okay.
And he's really the one who did most of the lifting on this, heavy lifting on this topic.
Okay, thanks. Try to find some more stuff. All right, thanks. Yeah, super. Thanks. Also, again, thanks, Matt, for organizing all these meetings. It's been great.
Yeah, absolutely. Thanks for having me, Matt. It was great.
Yeah, looking forward to the next one. So yeah, thanks, guys, and see you in September. Now let's grab some beer.
Come on. All right.
Sounds good. All right.
Yeah.
Hey, see ya, guys. Bye.